of contact and the difference, right? So who can tell me what the electrode is? Besides AJ, who works for me. Come on. I know somebody here. So how did we define the electrode? Anybody. Don't make me pick. Yeah, how did I define the electrode? How did I define the electrode? I defined it in terms of what we're going to use to carry the current out of our PV device, right? It's the thing that's got to have high conductivity, right? And then we talked about the contact. So what was the contact supposed to do? Especially in the context, actually, let's back up. So I checked how many people were physicists, how many material scientists, how many chemists. How many people in here actually make devices in their current work? Device folks, making devices, okay? All right, so now I know who to call on. Okay, excellent. Right, so the contacts. In the context of the bulk heterojunction organic photovoltaic device, what do the contacts do for us? Yes?
Provide carrier selectivity, so you can extract the carrier you want and block the carrier you don't want.
That's, I kind of like it, yes. I like it. I like it. I would make it more general, right? It's basically to break the asymmetry, right? In this, or to create asymmetry in the system, to break the symmetry. Because otherwise, right, if we're in this interpenetrating network that's a, goop, we become free carriers, we have no motivation to go anywhere except for back where we came, right? All right. So we also looked at this, right? And I tried to convince you that when we're talking about these transparent contact materials, electrodes and contacts in this context, we're talking about basically semiconducting systems, which we do the normal semiconducting games in, right? If we need it as an electrode, then we want to dope it heavily so that we can carry current. If we want it as a contact, maybe we don't want to dope it so heavily because that might cause recombination. But we wanted to basically provide these other properties that Cyrus, is that right? Cephas told us, just enunciated for us, which is we want them to basically pass the carrier that we want to harvest at that particular electrode, right? Contact an electrode pair, and reject the one that we don't. Right? But in terms of transparency, we had basically this behavior. And I asked, why is it, so we identified basically this onset in the transmission, i.e. the absorption above this, due to what aspect of the material? Semiconductors have what? They have band gaps. And so this here is due to the band gap, exactly. Okay, so then we have transmission. Anybody got any ideas about what these oscillations are about?
Interference.
Interference, that's right, excellent. Okay, then I start basically rolling off. What's that due to? Actually, because I asked this and I know that I got an answer from at least one person that was correct. So why is it we have basically this tail off here? What's happening?
We have absorption.
Well, yeah, so the absorption is in the green, so the absorption goes up, transmission goes down, reflection actually goes up after that point. So what's happening? This is free carrier behavior, right? So if we think about the conductivity, which is what we wanted for an electrode application, right? More is better, right? High conductivity. We want high conductivity, and we have this sigma is equal to mu n product. All right? So what happens to this free carrier absorption if I increase the number of carriers?
It goes up.
It goes up. Yes. And what happens if I increase mu instead? It goes down. All right? And so in terms of energy, what happens is that if I increase n, I'm going to change this absorption peak. In fact, that's just the same slide. This is what I get with mu. All right? So when I increase the mobility at fixed carrier concentration, I basically reduce that absorption peak, which functionally means what I'm doing is I'm opening this up. I'm essentially increasing the Q, if you will. right? Because the carriers here, the absorption is due to the carriers basically oscillating back and forth with the incident radiation, right? That's how we're getting the absorption. So if I increase the Q of those carriers, right, then I can open up this window. All right, I make it sharper. And if I make it sharper, basically this peak gets squeezed out. And that's what this calculation reflects. Yeah?
How do the free carriers absorb that?
Ah. So, how did the free carriers absorb? So,
I also want to make severe explanation. Why is the frequency breathing beyond like 1,000?
yeah.
Why?
Why?
There is a reason? Or?
So, the location of this peak is basically due to the number of carriers, right? So I can calculate that. And in fact, one way to actually determine what the carrier concentration is to look at what this wavelength is. Right, so why do the free carriers absorb? Collective motion, right? I mean, you gotta see a carriers. You're bringing in an electromagnetic field, right? You're sloshing them around. That means that they can basically absorb that energy. Now, if the Q is really, really high, right, they would absorb it and re-emit it, which is basically what we have in the situation where we have reflection, right? So the fact that we have width means that we have loss. Right? So if we have scattering, other things that are happening, then that's what's broadening up this peak. So if we increase the mobility, which is a reduction essentially of the scattering, then we sharpen this peak up, and we, like I said, open the bandwidth of the transmission up. Right? Now, to be fair, we don't change the location of lambda p. What we're really doing is changing how much absorption we see when we're not at exactly lambda p. Right? That's really what we're doing. But that does make a difference, right? Because if we have this, if we have some absorption here, that's just basically going to be loss in our device, right? If we're using this as a transparent window electrode, right? Everybody on board? Okay, good. Okay, so that's what, and this is basically the same calculation that I showed before, but now we're leaving mu fixed and we're changing the carrier concentration. So you can see this basically slides in, just like I told you. All right, so this is a slide that was requested. So, a lot of you guys make devices. When you buy, and a lot of you make organic devices? How many organic device makers? I wasn't specific enough. Organic device makers, okay. So how many inorganic device makers? Okay, so that's good. So for the organic device makers, I'm betting a lot of you work on ITO, right? Okay, so when you basically go to the vendor and say, I want ITO, what do you spec? Sheet resistance, right? That's exactly right. And so I've been talking in terms of conductivity, which is the inverse of course, the resistivity. And this slide basically outlines the relationship between the resistivity and the sheet resistance, which is what you spec. Right? So why is it that sheet resistance is the important number for you device makers?
You get losses if your resistance is too high, you already lose fault with.
That's right. Okay, because I didn't put it up, but you know what the solar cell JV characteristic looks like. So at high forward bias, if I have a lot of series resistance, what happens to that curve? It goes, yeah, which means that it actually, if it's bad enough, can impact my fill factor. So this tells you something about how the conductivity, i.e. resistivity of this layer, is going to be important in your actual device, and it tells you something about how large you can actually make that device, the area of that device, before you have too much electrical loss due to too much resistivity, or too much resistance in this layer. Okay, but there's one other important thing, which is, of course, so this is the sheet resistance, and all, you can see all this. So just to give you an idea, if I'm at 10,000 Siemens per centimeter, that basically translates to 10 ohms per square at 100 nanometer film. Right? But you notice that this is, of course, linear in T. Right? So if I double this, I'm going to have that. Right? Make sense? And the other thing I need to think about is, of course, the optical transmission. Because when I make something thicker, I'm going to make the optical losses worse if I keep everything the same. which is why when I showed you this, right, this is an 8,000 Siemens per centimeter piece of GZO, gallium doped zinc oxide, but it's also 500 nanometers thick, right? Which puts me kind of in the, 2 ohms per square kind of sheet resistance. But it is a little bit lossy, right? So these are the considerations. Are we happy with that? The requester, okay, excellent, okay. All right, so now I want to turn back to our PV device physics. PV device physics, basically very, very simple idea, right? We want to basically extract free charges from incident solar radiation, right? Photon in, electron and hole out. And just like yesterday, Maritz talked a little bit about degradation, in which case, and he said, well, okay, if you handle one degradation mechanism, then the next one on the post is going to be the one that now matters, right? That you've got to handle next. And there's this whole cornucopia of things. Same thing for the fundamental working principles of a PV device, right? There are all kinds of loss mechanisms, and we want to try and reduce all of them so that we can maximize our power conversion efficiency, right? Okay, so now we go back to the solution process, or we're going to look at the solution process nickel oxide, which is basically our canonical whole transport layer. Everybody remember why it was that we chose nickel oxide? No? Should I have included a slide? Maybe I should have. Do I have another one? Oh, yeah, okay. Yeah, here we go. Okay, so the idea was that we want to basically harvest holes out of this transparent contact electrode pair, right? So that means we want to basically pull holes out of the polymer. So we want there to be no energy differences here, or at least we want to minimize those energy differences so that we ease the transport out. At the same time, we don't want electrons going into that contact. And so if we have an oxide that has a nice wide band gap and is p-type, we can arrange for this alignment here, and we can arrange for the blocking up here for the in the full ring, right? Because both of the two constituents, donor and acceptor, have access to both of the contacts. So this is the kind of scenario that we said we wanted. And the claim was that nickel oxide should give us that. Now, I know you guys have heard, and we're going to talk about, a lot of other considerations in what really happens in the device, right? Things like morphology, the interface, whatever that means, right? But the thought is that while we have a pretty good whole transport layer in, by pretty good, I mean, it's got a lot of issues in PDOT, that these nickel oxide and other oxide layers would be better. Moreover, because the oxide is a nice semiconducting system where I have some tunability, when I go to something that's not P3HT, I should be able to basically match up the appropriate contact properties with that to improve the overall device performance. And then we went and we looked at this particular system, which is not the P3HT PCBM system, but is in fact the PCD TBT system, which was shown with this nice 6.1% power conversion efficiency by Heger et. Well, actually, Park et al., right? Heger's the last name. Park did all the work probably, right? So we should be Park et right. And then the question was that they had basically set up this particular device structure, right? These are the energy levels they proposed. Now, and the contention was that if we improved this particular interfacial electronics, or energy level alignment, that we could basically improve things. Now, do people think that that's a reasonable thing to do? Now, I've already kind of told you the story, right? And you all kind of buy it. But now the question is, was I just selling you something? Right? Was I just telling you a nice, convenient story, or is it really true? Right? I mean, it's all very plausible. Yeah? I wouldn't sit up here and lie to you, is what some of you are thinking, right? Well, okay. Now, so we proposed basically this kind of structure that we thought we could basically achieve with the nickel oxide. Now, what's one of the problems with the way that I've drawn this here?
You're not looking at sort of any energetic changes happening at the interface between the materials band name, interface dipoles, all that type of fun stuff they're not showing you.
That is exactly right. Moreover, I don't even know what it looks like. Right? I can measure all these things, and I'll show you the data. And I, in fact, have shown you, but we'll look at it again. All the energetics for these things, right? All these pieces parts. But I really don't know what the buried interface looks like. And one could ask the question, okay, what exactly do I mean when I talk about an interface? Right? But, okay, so the first pass, we could at least do this. This is better, right? Now we at least separate them out, because this is basically what we know. Right? And so, does everybody understand why I'm making a big deal out of this? Anybody have any thoughts? I mean, it could be, why is this guy talking about all this stuff? Right? Why could any of this make any difference?
Because you actually place P.PSS, which is one of the major reasons for degradation inside the devices.
That was one of my motivations, and I'll show you that I think that is borne out. But I guess what I'm getting at is, why am I making a big distinction between what the figure was before and what the figure is now? That's the specific question I'm asking about right now.
Well, you don't know how the interface works, and the interface will make a big difference. So putting it all together and being like, yeah, it's just a sharp interface, it's not really true. And you just heard earlier that like stuff can migrate between each other and you just don't know where stuff is at.
It's at the very least naive, right? And so, right, we're scientists. We're tasked with being, as thorough as we can be, recognizing that sometimes we won't have all the answers, right? We will do the best we can, but we want to be honest with ourselves about what it is we know and what it is we don't actually know. Okay, so this was the first attempt at a device with this system. And so you see that, okay, there's something I really hate about this. And so Xerxes, who was the author of this, knows that I hate it. But there are no error bars on any of these things, right? It drives me nuts. But one of the things you notice is that, okay, well, on the one hand, right, we've certainly increased the VOC here. That's consistent with what our kind of hypothesis was, and our motivation for using the nickel oxide. But do we know that that's really what we've done? Is there data in just this curve that says, yeah, the story that he told us is the one that's right? How many people think, yeah? Okay, we got one believer, too. Come on, AJ, you're supposed to be on my side. I would say, actually, it's not clear, right? Can't tell from just this. I mean, what else did we talk about yesterday? Moritz showed you a bunch of data, right? So how thick is this device? The PARP device, which is about the same as our device, is about 90 nanometers thick. Moritz showed you yesterday what happens when you change the optical spacer. So one question would be, what is the thickness of the nickel oxide? What does that look like compared to the P dot? Is that, okay, on the other hand, JSC looks the same. But that's certainly one thing we could worry about. What about the vertical phase segregation? Is there any? I don't know. Right? The contention would be that this is largely an unordered system. And we're going to make that assumption for the time being. And if you read the paper, that is what we assume. But one could ask serious questions about why is it that this system, or these devices, weren't as efficient as these. Could also be due to batch-to-batch variation, right, if we're honest. But if we look at these now, right, this is basically a much higher performance P.PSS based PCD TBT device. And when we replace it with the nickel oxide, we do even better. But those same questions could still be asked. Right?
I'm sorry, maybe I missed it before, but how did you code the nickel oxide? Is it spartan or soldier?
This is a solution process. So basically what we have is a metal organic precursor, and we heat treat that on top of the ITO. That converts it into nickel, a nickel oxide, I'll say that. One could worry about the structure, and I showed you that a little bit yesterday.
Okay.
But that's basically how we're generating it. And it's about 5 nanometers thick. 5.
Okay.
What are the N and K values of the nickel oxide?
Ooh, that's a good question. Why would I want to know that?
Well, you want to know how much light is actually coming.
Yeah, that's right. That's exactly right. That's an excellent question. We'll get to that in a second. All right? Did everybody catch what he asked?
No.
So he asked me what the N and K values are. He asked me what the N and K values are, because if I don't know that, then I can't possibly do the optical modeling to tell whether or not I've changed something about just the absorption properties. I mean, I argued that, well, okay, my current density didn't change much, so it's got to be okay, which is kind of a bogus argument, right? I mean, let's be honest. We're all friends here, right? Okay, so now I'm going to look at the dark JV characteristics. And this is what we see.
That's the leakage current.
Hmm?
The leakage current is
Yeah.
already a little bit lower.
Leakage current's different. That's consistent with the increase in VOC that we saw. Okay. And what else do we notice? If we look at the table. The resistance is different. In particular, the parallel resistance is very, very different. Which means we have less net leakage through the device. Now, that's consistent with what I told you was the reason why we thought nickel oxide would be good. Isn't it?
Electron blackening?
Yeah. Right? So that's a good sign that I haven't just fed you a line. Okay? What else can we notice? What about the value of n? It's different. Okay, how many people, raise hands, are upset by the value of n being larger than 2? Okay, well, at least somebody's being honest, come on. How many people are upset by an n value that's larger than 2? Okay, we got another one. Anybody want to share why?
I mean, we have to know the solvent of the active layer to say about it. Because it was fluorobenzene, maybe yes, we were upset. But we don't know.
That's interesting.
Yeah.
Why would that be upsetting?
Because fluorobenzene devices usually has an N value between 1.6 and 2, let's say.
Okay, but why is that reasonable?
I don't know. It's in the literature.
It's just how they end up. Okay, that's a perfectly fair answer, right? So yeah, N is the ideality, the diode ideality. I'm sorry, it's up here. So why is it okay for our ideality factor to be bigger than 2? Is it okay?
Wait, I'm sorry. I thought if the ideality factor is close to 2, you have trap limited transport, like that kind of thing. And it's just somewhere between 1.5 and 2.5 molecular combination. Like you could tell from the ideality factor it's bimolecular combination of traps. There's no limited what you have.
Yeah. So if the ideality factor is closer to 2, then it looks like more like bimolecular recombination versus not. How many people have read that and buy that? How many people have read Shockley's paper? Shockley Reed Hall's paper. So I would encourage you to do that. But what I will say is that one thing that we're assuming, right, when we think about ideality factors between 1 and 2, is we're assuming kind of an ideal diode, right, which has, along with it, a lot of caveats, which is why, as outlined in those papers, and it also assumes that we have one diode, right, one thing that's rectifying in our system. If we have 2 contacts that are both selective, presumably they're both rectifying, yes? which means we actually wouldn't necessarily anticipate that the values would have to be between 1 and 2. They may be, but we have more than one junction now. Right? So just something to think about. But, okay, assuming that these ideality values, I mean, okay, let's face it, we plus or minus 0.3, right? It could be 2, right? And we clearly see that when we use the nickel oxide, we actually reduce that, right? So we get closer to a more ideal diode. Yeah, I won't go into the details of what I think exactly one can read about N because, yeah, I'm not entirely sure whether I'm right. Okay? So all of this, I would contend, though, is consistent with the notion that we've improved the energetics in the way that I told you. But then the next question really is, I've done the solution process nickel oxide. I told you that I see no evidence for structure. When we have an amorphous system, what do we tend to have? I mean, we draw this nice band gap, right, that's nice and clean. But if I allow for there to be disorder, what does that imply, typically, when we think about it? Trapped states, states in the gap, right? One could actually wonder if it's an amorphous oxide, do I actually have a well-formed gap? Well, so that's why we turn to this spectroscopy. Now again, to be fair, here we've separated the two pieces parts out, right? So we're just looking at one component. But you see that when we do the nickel oxide, when we deposit it initially, you see the evidence for basically states near the gap that when we oxygen plasma treat it, go away. Not only that, we see that the gap essentially widens a little bit. And you see that the work function changes. So all that, again, is consistent with what I've told you about why we were trying to do, or what we were trying to do with the nickel oxide. So I haven't kind of fed you a line. At least this is our best guess for what's going on. And I think the data supports that. Now, I'm sorry, I digress here. But where's my, hold on a minute. Somebody asked me about NEK, and I thought I had the slide that showed that. Because that is a big question, right? If I haven't shown you the optical data, and shown you that the absorption, or the optical field is not about the same between the P dot and the nickel oxide, then you could basically disregard a lot of what I was saying. I do have that slide. If you want to see it, I'll show it to you afterwards. And in fact, it's in the paper. And where is my cursor? There it is. So okay, we'll start back up. But I think the point I'm trying to make is that we always have to be quite careful about all these things. And I have just completely swept under the rug this question about what the morphology and what the ordering looks like, right? There's nice data that I believe was taken by McGeehee and Tony that indicate for this system and this blend ratio, they don't see much structure. We know that the surface energies are not too dissimilar, and so we don't anticipate there's any difference, but to be fair, we haven't actually measured it. But hey, the referee didn't ask, so it's all okay, right? All right, and this goes basically what I was talking about disorder. So now I want to talk about this degradation question. So we just heard in the last talk, what happens to these organic things when we have carriers around? Yeah, the carriers are localized, that's fair. But nothing good, right? I mean, that's how you get oxidation. So I would contend one of the ways you can make your device more stable is by getting your contacts right. Because if you get your contacts right, you can sweep out your carriers faster than you can if you don't get them. Which means that the device should perform better. Now, in addition to that, as was pointed out, P.PSS also just bad actor, right? Does a lot of things we don't like. And while PCD-TBT is a much more stable system than the P3HG PCBM, which is what's shown in here, for the PCD-TBT, if we compare the nickel oxide and the PDOT device, we see that all the device metrics across the board are better, and they're better for longer, right? So this, I would argue, also basically supports that at the end of the day, when we've used the nickel oxide as this contact, we've done a better job of removing charge carriers from the active layer, which is what we want to do in a solar cell. Any questions? Everybody's on board now? Okay. Having said that, Moritz also warned us about extrapolating. And this is some device data that we took with Mike McGehee. Now this is basically just a bare oxide layer, and this is PDOT PSS. And you see that we get this kind of degradation here until we reach some critical point, and then it tanks. And this is the reference here. This was done work that was led by Matt Lloyd that we did about a year ago. And if I go back here, a lot of these, yeah, they're not bad, but we may not be far from catastrophe, right? And we just want to be aware of that. Okay, so the last thing I want to talk about is this question about the interface. What do we mean when we're talking about the interface? So, this is from the standard semiconducting textbook. So we know that when we bring a metal and a semiconductor close together, we get basically this band bending, depletion, right? This was mentioned previously. So the question I have is, what is it that we're talking about when we're talking about the interface? What does the interface mean to you? Trouble, oh, yeah, that's true. Any thoughts?
The local area along interface of both sides.
So this local area. So how would you define how far I should go away from something before I'm out of the interfacial region?
So anything different from the bulk.
Anything different from the bulk? Ooh, I like that. I like that a lot. So in our bulk heterojunction devices, we have large fields that are generated by our contacts. In which case, sorry, before I even go there. So based upon your definition, which I like, we would say that this whole area within the depletion width is not bulk-like, correct? Everybody would agree with that? So that means that based upon the proposed definition, which I like, you guys may not. I haven't heard any objections, so we're going to go with it. No objections? Speak now or forever hold your peace. No? Okay, all right. The question we could ask is how much of our device in a working device looks like this depletion width or this depleted area, i.e. we have essentially band bending, non-flat bands due to the details of our contacts, versus how much looks like flat band and bulk.
That depends on the thickness. Because if the thickness is too small, we are not going to see any band bending.
That is absolutely true. And how thick are these devices typically for these high-performance polymers? 200 nanometers. Actually, I would say that there's somebody that's sitting here, or here, in this area, who's done some measurements, or a collection of people actually, I guess, who've done some measurements that look at what the depletion width looks like. And I think that if you look at that data in comparison to what your typical device thicknesses are, you would say that it's all interface based upon our definition. So just keep that in mind. All right. Yeah. These guys, this paper, have a look. That wasn't their main intent, but I think it actually demonstrates the point I just made quite nicely. You can ask them about it. They're here all the time, right? Okay, so.
Everybody was writing it down.
Oh, sorry. Get the important bits. Advanced Functional Materials, volume 21, number 13. These pages, last year, May. Now I can't vouch for the reputability of these particular folks, but so far I tend to believe what they tell me. Sometimes. All right, so now here I have a quite thin layer, and I've just made it. So this came up when the Dr. Lee, right, when Gang Lee was talking a little bit about how is it that some of these deep N-type things can work. Okay. So here we have one oxide whose conduction band is very, very far from vacuum. And we have an interface with P3HT. And then we have an aluminum contact. Now, to be fair, this is quite thin, but you can see the band bending. And you can see that, yeah, this should be not bad for holes. And here, well, we'll get to that in a second, right? Well, here, I think you'd all agree that this is not going to be a great way to transport holes out of my device, right? Because a hole would kind of float up. It wouldn't float as fast because the slope isn't as good. And once it got to here, presuming this is, right, given where the Fermi level is, it's got to basically make it into here to go anywhere else. That's going to be the lowest energy drop. But it's still significantly larger than what I see here. Well, so given what we talked about yesterday, I went and did this last night. And this is for moly oxide with most of the parameters coming from Antoine Kahn's work. And this is zinc oxide based upon some of the stuff that AJ's done and we've done at NREL to characterize some of our systems. Right? Now, to be fair, right, if we drew in the acceptor, okay, you know, we'd have another electronic level, but it wouldn't really change this picture. Because I haven't assumed anything, I haven't worried about any of the details in here. I've just looked at basically what the band offsets are. Very simple calculation, and I've given it some typical carrier concentration. I haven't worried about, you know, reorganization energy, what happens when a charge carrier basically moves from this polymer into this oxide, because they aren't the same, right? So there are all these additional energy terms that I would really have to consider if I really wanted to understand exactly what's happening in the system. But at the end of the day, if I know enough about those different energies, I should be able to calculate a rate, and my contact could be viewed as selective, I would contend, if the rate for the charge carrier of interest, in this case holes, is higher than that of electrons. That's the simple definition, right? If I make a contact that makes my device, or at that interface, or in that region of the interface, although now we're recognizing that that may consist of most of the device, if I make the contact in such a way as to essentially enhance the extraction of holes out of that side, I've basically improved my device. And I think if you look at the device physics in total and think about things like quasi-Fermi levels and other things that people talk about, it all boils basically back down to this notion about how fast are you removing these charge carriers versus how fast are you allowing them to recombine. I mean, I would argue that it has to, because it's physics, right? That's the way physics works. All right, and this is for nickel oxide. So, on the one hand, the moly actually looks better than the nickel in terms of basically providing a path out for holes, because at least the way I've got this set up, right, there's this kink. That wouldn't be good. Now, to be fair, if I went to a system like PCD-TBT, where I could lower this, now the nickel oxide may be better than the moly, right? But just picking a P-type oxide isn't going to make the world perfect, right? We really do have to match these things up energetically, and we have to do some kind of accounting for all the different energetics in the system. Now, we may hide a lot of those energetics in things like, you know, surface states. Well, so let's talk about that, right? What happens if I have a bunch of defect states here? What are they really going to do? Or what kinds of things can they do?
Combinations.
They can do recombination. They can basically cause charge carriers near that interface to fall together. Okay, that's one thing. What else can they do? They can disturb the electric field. They can scream, right? They can change the thermal resistance, right? So they could affect some of these other ideal diode parameters that we have. And if you think about those things, given our definition of interface, one could worry quite a bit, and basically what I'm looking to do is caution you. When you read work that talks about interfacial recombination. What does that mean? What does that mean? Now, there's some very, very beautiful work where they talk about, they model recombination as a recombination velocity. But keep in mind, if you look at those kinds of papers, most of the people who do a really nice job of it, and there are a number that I like, I can't remember their names right off the top of my head, and I certainly can't pronounce a couple of them. They talk about a surface or interfacial recombination term that they've modeled. That doesn't mean that the recombination in your device is actually happening at the junction between these two. It's happening in the interface as we've defined it, which means that it could be happening essentially in what some people might consider the bulk of the active layer, or throughout the active layer. So the way I tend to think about it is, if we change things at this interface, we can have interfacial precipitated recombination. But that's about all we can typically say, unless we have really nice experimental evidence that points exactly to where it's happening in the device. Is it happening in the active layer between basically what we would normally consider kind of bimolecular recombination, because basically the carriers aren't getting out? Or is it really happening through some trap states on, or at one of these oxides? And the physical interface between, say, the orbitals of the polymer and the, outer electrons of the oxide atoms. Quite honestly, I don't know. I'd love to be able to look at that, but it's not an easy thing. Okay, so, and this is kind of the example, right? IZO is an amorphous oxide, has properties that are quite nice in terms of electrodes, has very similar kind of electron affinity, work function, what have you, to zinc oxide. We can dope it heavily or not so much. And so if all of the things in the world were equal, you'd think it should work the way zinc oxide works as an ETL in an inverted solar cell. But this is data from AJ that clearly shows you that it doesn't work like an inverted solar cell based on zinc oxide. And so the question would be, why is this? Now, on the one hand, I would love to be able to tell you that this is interfacial recombination. But again, I don't actually know what it is about the interface that changes what the device looks like from a device physics perspective. So I can't actually tell you that. But I can tell you there's a massive amount of recombination and it's a crappy device. All right. So with that, I'm going to close off this section. Thank all these people here who are the people that I work with on day in and day out basis across the ZFRCs. And now I'm going to go to the last thing, which is completely different. Am I beyond time? Do people care? I was going to tell you about the optical rectenna.
You have it on its own right now.
Oh, do we? All right. So sorry, you guys. You guys won't get to hear about the optical rectenna.
You got 2 more minutes.
2 minutes? Okay. All right. Optical rectenna. So the basic idea is that this is the optical rectenna is a device that basically takes incident light, runs it through a diode, right? Because we just talked about it. At some level, an AC alternating signal, right, at kilohertz, like what you, or hertz, like what you get out of the outlet, right? We know how to rectify that, make DC out of it. So light is no different, except it's much higher frequency, which means that we need a much faster diode. And so the optical rectenna is basically a concept which has been demonstrated actually at intermediate frequency ranges, right, for gigahertz frequency signals, but hasn't been demonstrated for light. Has an extremely high power conversion efficiency at over 80%, but requires a number of breakthroughs in order to actually realize for solar conversion. We got to worry about how exactly we're going to have a optical frequency antenna, but there's somebody that's going to talk to you about that in a couple days from now. Then we need to have a waveguide, and then we need to worry about the diode. And the diode, in this case, could be, there are a number of different ways to do it, but the fastest diodes that we have these days are basically based on metal insulator metal kind of geometries. So it's kind of cute because in some sense, right, I mean, this is a device that's all contact, right? There's nothing else. And the operational frequency is dependent upon this. So we need to basically minimize this capacitance. So one of the things that we've been doing at NREL is looking at what are really the design rules for to essentially build one of these ultra-fast rectifiers. And to be honest, even if we can't get it to work at solar frequencies, so optical frequencies, there are a lot of interesting things that we can maybe think about doing with it, even in the kind of what would normally be considered very, very far IR/terahertz regime. And the basic concept is this, that we have this insulator, we have two metals, and we want to basically couple these two with our incident radiation and move charges across. So if you think about what you need to do that task, you want a diode that's close to the ideal, that is to say it turns on really, really nice. And you want to maximize these figures of merit, right? We don't want to have something that's symmetric. We don't want to have something like this because the turn-on voltage is way too high, right? And if all we've got is a single photon to do this process with, that's going to be a problem. So we want what we call the nonlinearity to be super high. We want the asymmetry, right, between forward and reverse to be high as well. So we want something like this. And it turns out that people have been looking at this for a long time, and these are some of the candidate materials, but no one has really thought about what it is at kind of a basic material science level that we really are trying to engineer in this. And so the talented graduate student who's done a lot of this work has basically found a way to do the screening using a point contact, which has been done in the past, of course. People have made point contacts and have demonstrated them to rectify at very, very high frequencies. But he used this along with a set of particular choices of these MIM constituents in order to look at what happens when he changes essentially the work function of these two metals and the insulator. Now, because of time, I'm not going to go through all the details, but suffice to say that we've been able to basically put together, oh, that's unfortunate color choice. What we really want is not a system like this, but a system like this. Because if we have a system like this, when we have the incident photon, it essentially modulates and allows us to couple across here very, very efficiently. And because of time, so it gives us this asymmetric response that we like, although this is done at DC. And so we can basically begin to put together a material space of choices of work function and electron affinity for the insulators and the metals that essentially maximize the figures of merit that I told you about before. So now, to me, this optical rectifier is kind of an interesting concept because, you know, exactly what's happening when we talk about coupling across this insulator at kind of a very fundamental level is kind of an interesting question. Things like the orbital asymmetry of the metals could matter, for example, to how well that performs. Not only that, the details of the interface, all these things that we kind of sweep under the rug a lot of times, they matter explicitly for these kind of devices. People work very, very hard to make them very, very clean. So with that, because of the time, I'm not going to go into the details, but I will just throw up this particular paper, which is where we go through all this stuff that I haven't been able to tell you about in detail because of time. So I'll leave you with that, and I thank you for your attention. I hope it's been informative or at least interesting.
So, a couple of questions?
Yeah, I would like to ask, what kind of PSS did you use for this work?
Oh man, I'm totally not the right guy to ask that question.
Because the data that you show us indicates that maybe the nickel oxide has more or decreased sheet resistance.
Yes.
So I wonder if a highly conductive PSS like PH1000 maybe
Yeah.
be a better.
No, we are definitely using. We're definitely using one of the more insulating versions. I can't recall the exact details. That's something that, like I said, I'm kind of the wrong guy to ask, but I think I have it someplace in one of my notebooks. AJ, do you know offhand? Yeah, so apparently it's one of the Plextronics varieties.
Okay, yeah. Okay, maybe the other question is confidential as well, so.
Well,
Yeah.
but at the end of the day, actually, we've made devices with a number of different PDOTs, and that doesn't seem to help, right? And in addition to that, I mean, given what our device architecture looks like, so I think your criticism or your critique, shall we say? Oh, I'm not saying you're criticizing, but the question you're asking is an interesting one. But given the way we've basically structured the experiments, we've kind of controlled for that. I didn't go into that in great detail,
because
but
I have some experience with these oxides, and I know that many of them are UV activated or are photo annealing activated. So
Yeah.
I was wondering all these things. If you guys made an oxide that is working better than a highly conductive PID or PSS, that would be
yeah. So I would argue that the nickel oxide is going to work better for the appropriate active layer
okay.
than the PDOT PSS. And what I would basically advocate is that the thing that we like about the oxides is the degree to which we can tune some of their properties. Now, one of the things that I also didn't get to talk about in detail, but is this question of what's really happening when we do the oxygen plasma treatment, right? So I showed you that there was a change in the density states, opening up at the gap, changing the work function. Presumably there's also a change in the carrier density, but that's very, very hard to measure in these things. But one could worry about, well, if I've really done that, why haven't I if I've really generated more carriers, which is why my work function is going deeper since it's P-type, why haven't I also made recombination worse at that interface, right? That's I mean, a perfectly legitimate kind of question. And to a certain extent, I'm not entirely sure. I would say that the more instructive case to kind of illuminate some of the questions that you're asking is actually what we are working on the ETL side with zinc oxide, because we can tell a lot more about the physical properties. And I didn't talk as much about that because I just had to pick something. So, but I would refer you to AJ over there, actually, who's doing a lot of that work. So we have basically looked at differences in carrier concentration, differences in mobility of zinc oxide, and what impact that has on how well we're able to get carriers out. Sorry.
Thank you.
Okay, well, let's thank both speakers.